Now that we've looked at how to solve the n order ordinary differential equation with constant coefficients and for the homogeneous case, let's look at some applications. And the simplest, pretty interesting application is again the harmonic oscillator. And because it's homogeneous, well, this is a force-free oscillation, so it's a free oscillation. So I'll review the problem, and we'll review the problem in the context of a mass on a spring, as opposed to the electrical circuit. And we'll derive the solution and look at the different types of solutions depending on the size of the various forces. The first is a drag-free oscillation. The second is a damped oscillation, and I'll refer to this as a bad shock absorber. And then we'll look at the case of a critical damping and over damping. After seeing the video, the goal you should have in mind is that you'll be able to find all types of solutions for the damped free oscillator, and then importantly, relate the mathematical solutions to the physical behavior, and hopefully gain some insight into the mechanical behavior of the system. So again, we have a damped free oscillator. And let's review the problem of the mass on a spring. So here we have our fixed wall or whatever is holding our spring. And so here's our spring. And again, we had a mass, M, that was sort of resting on top of a viscous fluid. And the force of the spring was the spring constant times x, where again x is I guess x equals 0, where the spring is neither stretched or compressed. So if the spring is stretched, where x is positive, then the spring force will be back towards the wall, and that's drawn by this arrow here. Let's see. The other force is the force of the basal of the fluid. So this is the drag of the fluid, and that depends on, for example, the layer thickness of the fluid or the viscosity of the fluid. And in class we talked about this fluid as being like pancake syrup. So we have mass on a table resting on top of sticky syrup. And the drag force on the fluid is equal to c times the speed, the velocity of the mass. So that's x prime. And then in general, we may have a force, an applied force. This is our external force. So this is someone pulling or pushing on the mass. And then so with those forces acting on our mass, we have um, mass times acceleration. Acceleration being uh, x double prime, and so x is our position and time is our independent variable, and so x double prime is the second derivative of x with respect to t, right? So that's mx double prime. That's the acceleration term, and that's that plus the drag force plus this force of the spring is equal to the external applied force. Okay. So that's our force balance equation. And here we're going to consider the homogeneous case. So um, that is, any function independent of x means that the force, which is in general a function of t, is equal to 0. So we're not pulling, nothing is pushing or pulling on the mass except for the spring and the table. There's no external force. And so that's why this is a free oscillation, or a free oscillator. And so our equation, so that gives the equation m x double prime plus c x prime plus k x is equal to 0. So it's a second order ODE with constant coefficients and it's homogeneous. And the characteristic equation becomes x double prime converts to lambda squared, because again we're assuming x is proportional to e to the lambda x. And if we take the second derivative of x, sorry, this e to the lambda t, and if we take the second derivative of x with respect to t, we'll get a lambda squared term. The second term in the characteristic equation is c times lambda, plus, and then the last term is just k is equal to 0. And so this gives the solution that lambda is equal to minus c plus and minus the square root of c squared minus 4mk all over 2m. That's the general solution for the free oscillator. So let's consider the case in which the drag force is 0. And I better move to the next page so I have enough space. So here, so the solution is again minus c plus and minus the square root of c squared minus 4mk all over 2m. So the special case that we'll consider is when there's no drag. So there's no syrup on the table. The coefficient on the drag term is 0. And in that case, we have our solution being lambda equals plus and minus the square root of minus 4mk all over 2m. And that gives, because we have a minus in the square root term, we have an imaginary solution, and that's plus and minus I times the square root of k over m. If we pull the 4 out of the square root sign, we'll get a 2, and that cancels with the 2 in the denominator. And we can also write the solution as I omega, where omega is that's equal to the square root of the spring constant over the mass, and this will turn out to be a angular frequency. So remember, when we have an imaginary root, we have an oscillatory behavior. We have sines and cosines, and omega is the angular frequency of that oscillation. So the general solution is x is equal to one constant. We'll call it a this time. Last time we called it c1, but we'll call it a this time. E to the positive I omega t plus b e to the minus I omega t. So that's the general solution. We could also write that as x is equal to a different constant c times cosine omega t plus d sine omega t. Remember, we can write e to the I omega t in terms of cosine and sine. So this is an equivalent form of the solution. And yet a third equivalent form using a trig identity is e times sine omega t plus some arbitrary angle phi. So we go from here to there using a trig identity in which the a cosine function and a sine function can be expressed as the sine of the addition of two angles. And here E is equal to the square root of c squared plus d squared. And phi is an angle, and that's equal to the arctangent of c over d. So this is just a constant. This is our second constant. Remember, we're going to have two constants. In this second form, it's c and d, and in this third form, it's e and phi. So the solution here, let's sketch the solution. So here's our time axis and our displacement axis, x. And we might start at a starting position, x0, and we'll have an oscillation that's some periodic function that looks something like this, perhaps. And I should note that the starting velocity, the slope, is x prime at time equals 0, and let's just call that x prime sub 0 or something. So here's our initial conditions. Our x at 0 is equal to x0, and x prime at time equals 0 is equal to x naught prime. And so the mass will, if we send it moving forward at this starting velocity, at a starting position, it will oscillate back and forth because of the spring. And since there's no drag force, it will just oscillate forever, theoretically forever and ever, right? We have no drag, absolutely zero drag force on the mass. It will just oscillate forever. And so, in reality, it'll be very hard to set up a mass without any drag. So it will eventually stop oscillating. But this is the ideal case in which there's actually absolutely no drag. And the period is the time between two peaks. So the period is, we'll call that capital T, and that relates to the angular frequency as 2 pi over T. So the angular frequency tells you that the oscillation spans a full circle, 2 pi radians in one period. So the angular frequency is radians per second. And you should note that the angular frequency increases with the stiffer the spring is. The stiffer the spring is, the quicker the oscillation will be, and it decreases with the mass. So the more massive the mass is, the inertia of the mass will be important, and that will tend to slow the oscillation. So again, that was the special case in which we had absolutely no damping fluid or drag on our mass. Now let's look at some different situations, different solutions for different amounts of drag on our mass. Now when C is not equal to 0, then the solution or the behavior is very sensitive to the value of what's under the radical here. If what's under the radical is greater than 0, that behaves very different than if it's less than 0 or equal to 0. And what is key here is how large c squared is compared to 4mk. And so we'll define 4mk as a critical coefficient, or critical damping coefficient, or I should say, yeah, the square root of 4mk is equivalent to a critical dampening coefficient. So let's look at the first case in which C is less than this critical damping coefficient, square root of 4mk, or C is less than this critical value. And we'll refer to that as underdamping. So when C is less than this critical value, then you'll see that what's under the square root is negative. And when we take the square root of a negative number, we get a complex root. So lambda is equal to minus C over 2m plus and minus the square root, or I, the square root of negative 1, times the square root of 4mk minus C squared over 2m. And that gives rise to x. If we raise e to the lambda t power, we get an exponentially decaying term, e to the minus c over 2mt. And if we raise e to the I times a number, we get using Euler's equation, we get a cosine and a sine function. So I'll go ahead and write that as cosine of the square root of 4mk minus c squared all over 2m, and that's multiplied by t. And then we get our sine term, which is, we'll put the coefficient as being b, sine of all of this. And so we get a function that's partly periodic, but the amplitude of the periodic function is multiplied by, is an exponentially decaying function. So if we were to sketch this up, we're going to sketch x as a function of t. The envelope of the periodic function is controlled by this exponential decay curve, e to the minus c over 2mt. And again, we're starting off with an initial velocity and an initial slope, x naught prime, and an initial displacement, x naught. So starting off with our initial velocity and location, we get a periodic oscillation whose amplitude is modulated by this exponential function. And so this basically behaves as a bad shock absorber. If you're driving in a car and your car hits a bump and it behaves like this, you're going to be oscillating for a while, governed by this exponential decay. So now let's consider the situation in which our damping coefficient is equal to this critical value, which is the square root of 4mk. In that case, what's under the radical is 0, and therefore lambda is equal to minus c plus and minus 0 divided by 2m. And if we substitute square root of 4mk for c, then we get minus the square root of 4mk over 2m, and that equals minus the square root of k over m. So in this case, we have only one root for lambda, one value for lambda, and so we therefore know that lambda is a root of order k. And k is equal to 2 in this case because it's a second order differential equation. And so we have a repeated root, and so our solution for x is equal to, well, it's proportional to e to the minus c over 2mt. But since it's repeated, we need first the constant coefficient, and then we have to add a linear function of t. So we'll say b times t. So here we have a linear increase in x with t multiplied by an exponential decrease. So it turns out that the linear increase is important when t is small, when the exponential part is small, but eventually the exponential part takes over. So if we plot our solution, or sketch our solution, again we assume an initial velocity x naught prime. Okay, so we have our initial velocity and location x naught, and in this case again the linear increase is important in the beginning, but eventually the exponential decay term takes over, and the block of mass, the displacement decreases exponentially to 0, and it eventually settles down to 0 as t gets very big. Okay, so this is a case of critical damping. When c was equal to the critical value. And finally, let's consider the case in which c is greater than this critical value. And this describes overdamping. So when that's true, lambda is equal to minus c over 2m plus and minus, plus or minus, the square root of c squared minus 4mk, and that's positive and real, divided by 2m. And so here we have a solution. Our general solution is first we can break this into two parts again. A part that's an exponential decay. That's this first part. And then we have two solutions representing the positive of this. So this is a e to the positive square root. I'll put everything in the square root in, represent that in parentheses, all over 2m times t. And then plus, so this is the positive exponential growth term. And then we have the negative square root, which represents another exponential decay term. And note that since we have real exponents, a positive exponent and a negative exponent, this could equivalently be stated as a sum of a hyperbolic cosine and a hyperbolic sine. So this case of overdamping, if I could sketch that, again starts off at the same velocity, our initial velocity, but it doesn't peak as high, and it takes slower to decay. So this is overdamping. And I'll refer you for the precise plot to figure 4,
page 113 of Greenberg of our textbook. So please have a look at that. So to recap, we have our mass on a spring with a damping term. And if the external force, the external force on the mass is set to 0, then we have a free harmonic oscillator. And this, the behavior of the oscillator depends on how large this coefficient, this drag coefficient is. If the drag coefficient is 0, then we predict an oscillation, a periodic oscillation that just occurs forever. That mass will bob back and forth forever because there's no drag. If, on the other hand, C is non-zero, but it's less than the critical value, then we get an oscillatory behavior, but the amplitude decays to 0, and eventually the mass will come to rest. If C is equal to a critical value, the critical value, then we get the product of a linear increase in displacement versus time and an exponential decay. And eventually the exponential decay wins out, and again the mass slowly goes to a 0 displacement and eventually stops moving. And the behavior is similar if we have an overdamping case, except for we have a product of two exponential decay functions in general, but we may, depending on the initial conditions, also have a exponential growth term. But eventually the exponential decay wins out, and that's shown by this yellow curve. Okay, so that concludes this discussion of the harmonic oscillator with free oscillations.